A simple TCP client application. So what we are going to do in this experiment? Right now I have opened two applications. The first one is the real term, and this will help me view what is going inside my microcontroller over a serial line. And here is the software Hercules, and using this I will open a TCP port on my PC, on my computer. And for that I have gone to this TCP server section, and I will open and listen to port 5000, and here is the received data section, and here I will view all the data that is coming from my STM32 embedded host. So let us start listening to the port 5000. So now Hercules is acting as a TCP server and it is listening to port 5000. Now I will go to my embedded host and start it, and you can go what is going inside my embedded host here in the serial terminal real term. So let us start. 1 2 3. Data sent successfully. Here you can see the data is received on the TCP port. So this is our example. This is the example of our basic TCP client. In this case our embedded host is acting as a TCP client. So now let us see what is going inside my embedded microcontroller. So first it is trying to connect to the server, and here is the message connecting to the server. At this point it is trying to connect to the remote server, which is my PC, and this is actually the server software TCP server Hercules, and it is listening on port 5000. So next we can see the success message that our embedded host is successfully connected to the server. I means this my PC which is running this Hercules server, and then my embedded host, my STM32 will start sending data, and I have taken a loop of 5 so that we can view the messages coming here. So it is sending data one by one. First time sending data to the server, data sent successfully. At this moment we will see that data is received here, and it is sending the same hello message, that is hello from STM32 5 times, looping 5 times. So now let us once again run this program. I am clearing both the terminals like this. Now I am restarting the application once again so you can be clear about the concept. Here you can see hello from STM32, hello from STM32, hello from STM32, data sent successfully. Like this it is sending. Our embedded host is sending data over a TCP connection, and we are able to view this data here on the TCP server. So in this lesson, in this video lesson, we will learn how to code this simple application. So here you can see the structure of our program. On the left hand side of the screen we have our embedded host, which is at the IP address 192.168.2.21, and on my right hand side I have the PC host, whose IP address is 192.168.2.17. These we have discussed in the previous lesson. And in our PC host I have opened the TCP port on port 5000 using the Hercules application, and we are listening on port 5000 for incoming connections. So in our embedded host, our application program requests lwIP to establish a connection to the IP address 192.168.2.17 on port 5000, which is our PC host, and this port 5000 is opened using the Hercules software. It says, okay, I am trying, please hold on, and our TCP IP stack tries to establish a connection to the provided IP address and on the provided port number. And after success it informs our application code like this, that we are connected, and the connection here you can see using the red line, the connection has been established, and now we can exchange data. And in this example our application code sends simple text messages using this channel, and these are displayed in the terminal screen of the PC like this. A message from STM32, again few messages from STM32. So this is the overall structure of our application program, and this is what we are going to code in this lesson. So now let us start coding. Open your STM32 cube IDE and load the main.c file for editing. So the very first thing that we need to do here is increase the stack size of the default thread. This is the default thread in which we are running our application. We are writing our application code. So here is the attribute for our default thread. It is somewhere around line 71. So by default, when we create a new project, it allocates this much of stack size. So this is actually 128 multiplied by 4, which is 512 bytes of stack. But this stack is too small to run our this TCP IP based application. That is why the first thing that we need to do is to increase the stack size. So minimum what we need, the minimum stack size should be at least 1024 bytes. So we should at least multiply this 128 by 8. So this much amount of stack is minimum required. So the first thing that we will do, we will increase the stack size of our default thread, and then we will scroll down, and let me do a small experiment now with the code that we have written in the previous lesson. We will not change anything. Just I will put a breakpoint, and I will go to our default task. This is the default task function. So what I will do, these things we have written in the previous tutorial, in the previous lesson. So here I will put a breakpoint just after this netif config, and then run our application, debug our application. Program is flashed and ready to run. My pointer is here. So let us resume the program, run the program using the debugger like this. Now the program is running, and now it has reached our breakpoint here. So what we will do here, we will analyze the tasks that are running in our system. So for that, go to this window menu and go to this show view, and under this free RTOS section, go to the task list. So what are the tasks running? This is the default task where we are running our application code, and this one is the idle task. This is created by default by our operating system, and this is the netif task that we have created to handle the interrupts, and this is actually fetching the packets from our ENC28J60 chip and providing it to the TCP IP stack. So this is actually using as an interrupt handler. The interrupt handler is delegating its job to this task because it is good practice to keep the ISR or the interrupt service routine as short as possible. That is why we are not doing heavy lifting inside the ISR itself. It is just signaling the semaphore, and the semaphore is releasing this task, and the rest of the task, the rest of the interrupt processing is carried out inside this netif task. And this task we have discussed in the previous lesson, and we have created in the previous lesson. Here you can see the definition, this one. The name of this task is netif, and this same string, whatever string, the name string we pass here, this is displayed in the task list. And this one, the TCP IP, this is the most important task running on the system, and this task is created actually by the lwIP. And actually this is the lwIP task, and this is doing all the TCP IP related processing. And last one is the timer service task. This is also by default created by FreeRTOS. So in this system, the tasks that are created, this one is created by lwIP, and this one is created by us, and the default task is also created by us. So in this way we can analyze the tasks that are running in our system, and if you can see this task running, that is netif and TCP IP, that means you have configured the coding well and everything is running very good. And now let us go to the coding part. So I'm stopping the debug. Now go to the start default task, and here we will add our application code, the application code for the simple TCP client. Here we will add the code. So where is the code? It is inside the thread function start default task, and these things we have written in the previous lesson, and here we will add the new code. So let us start. So the very first thing that we will do, we will need the IP address of our server or our PC which is running the Hercules server application. So we need to declare a data structure, and this data structure is declared like this. It is IP address addr underscore t, and this is the data type, and this data type is defined by lwIP, and this is our variable server IP. So here we will keep the IP address of our server to which we will send messages. Then we will define our next data structure, and this is like this, and the name of this data structure is status, and the type is err, that is error t. This data type is also defined by our lwIP stack, and this data type is returned by most of the networking function, and this is the return code from which we can know whether the function has succeeded or failed. And next we declare one more data structure, and this is like this. The name of this data structure is CONN, and this is short for connection. So this will represent our connection, active connection. To hold the data related to a connection, we need this structure, and the name of this, the type of this structure is netcon, and this is also defined by lwIP. So here you can see that this is just a pointer. So as this is just a pointer, we need to actually allocate this actual structure, and this is done like this. This is done using the API function called netcon_new, and the parameter is like this, netcon underscore TCP. So using this function we can either create a TCP based connection or a UDP based connection. So right now as we are creating a TCP client, that is why we are using a TCP type here. And whatever this function is returning netcon new, this is the part of the lwIP API, and we are storing it here on the con variable like this. Next we will initialize the IP address of server like this. For that we will use a macro like this, IP4 underscore ADRR. So this 4 stand for IP version 4 or IPv4. For simplicity we are not using IPv6. And what are the arguments? So here is the server, we are passing the address, this is the seize address of operator, so we are passing the address of this, and here we will putting the IP address in a standard notation, that is 192.168.2.70. this is the IP address of our PC where we will be running our server application. So this will populate this data structure. This macro will actually populate because this is uninitialized here, so this is initializing it with this IP address. Now this IP address is ready to use. After that we will call a API function to establish the actual connection like this. First I will do a printf to notify the user that what is happening inside our microcontroller. So it will print a message connecting to server like this, and then I will call the actual API, and the name of this function is netcon connect. So this is very user friendly name, as we are trying to connect, we are calling this connect function. And every function in this API group, it is preceded by this name like this, netcon. We will discuss it in the next lesson. Netcon. This is actually the name of the API that is exposed by our lwIP. This is called the netcon API. And this netcon API is very similar to the BSD socket style API, although it is not 100% compatible, but this is similar. This netcon API is specially crafted for small embedded system which has limited processing power and limited RAM. That is why we have an alternate API which is similar to a standard API. So what we are doing here, here you can see the status which we have declared here like this. So we are receiving the return value of this function. Whatever function we will call, we will use this variable to hold its value, status. So status equal to netcon connect, and the first parameter we are using the connection, this connection, and the second parameter is the IP address to which we want to connect, and we are using server IP which we have initialized here, and the third parameter is the port number on which we want to connect. So after that we need to check whether this connection established or not. So there may be several reasons why this connection may fail. For example, if you are not connected, actually the Ethernet cable is not connected, then this function will fail. Or if everything is connected, cables are connected, but this server is not up and running. For example, your PC is switched off, or your PC is not running that Hercules application. But even if it is running the Hercules application but has not opened the server port for listening, then it might fail. That is why we have to check whether this connection actually succeeded or not. So we will do it like this. We will check the status, and if it is equal to error okay, that means it is okay. Don't be confused by this error name. All the return values they are preceded by this ERR, prefixed by this. So you can control and click on it to see various other options available like this. So if it's equal to okay, then we print this message like this, printf connected to server. And on the other hand, if our connection fails, then we print something like this, sorry, could not connect to the server, and we go inside an infinite loop because we cannot do anything if we cannot connect to the server. Then what we will do after a connection establishment, we will send messages, simple text messages to our server, which will be displayed on the terminal screen, on our PC screen. So here is the code for that. Send a hello message 5 times, and we will send this message 5 times so that we can clearly view on the terminal. For that I have taken a simple for loop here. So before sending any data, I am informing our terminal, that is serial terminal, that we are sending data to the server. So better we should write this code like this. We should again use the status variable, and we should hold like this. We have to use this simple function netcon write, and netcon writes to the active connection. So the first parameter is to which connection to write, and the second argument is the data, whatever data which we want to write. So here I am sending a simple text message which is hello from STM32 and new line characters. And the third parameter, this should be the size of this data. So you can count it here like this: 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So actually it is 16 character plus a CR-LF pair, which adds 2. So 16 plus 2 is 18. So we will send 18 bytes of data like this. And the third parameter is the mode of sending this data. Right now we will not go into the detail of this, just type this netcon underscore no copy. And then again we are analyzing whatever happened to this function return values. So we will check this status. If status is not equal to OK, that means we are unable to send data to the server. So we will print a failure message. So here sending has failed, so we have to print some message like this. Sending failed. And then we delete our netcon using the netcon API, netcon underscore delete, and pass it which connection to delete. So this connection, and then again we go into an infinite loop. On the other hand, if it returns OK, we print the success message like this, data sent successfully. And before looping over again, we implement a 1000 millisecond delay, that is about 1 second delay, and this is the end of our loop. Like this, we are using this loop to send this message hello from STM32 5 times to our server. And finally, after the loop, what we do some cleanup. And the first thing is that we close the netcon, close the connection, close the TCP connection that we have started here. Netcon connect, we have connected here, and we are disconnecting here. For disconnect, we have to call this function netcon close and pass the argument the connection which we want to close. And finally, we actually delete the resources associated with this new connection that we have allocated here on the netcon new. Here we have allocated some memory for this new connection which we are freeing here like this. So that's it, this is the program, and now you can easily build it and debug it to see the output. So I am able to compile it without any errors, and now you can debug it and view the outputs. So now let us first download Hercules. For that, just go to your web browser and type Hercules terminal and open up this page from HW group, Hercules setup utility. So here is the download link, just download and run this utility. So this is the user interface. It has several options, but for this example just go to the TCP server section and here enter 5000 as the port number and just click listen. And if there is some pop-up from your firewall like Windows firewall or some antivirus, just allow this port, otherwise you will not be able to receive data here. And in the extreme case, if you are not able to receive data here, just for 5 or 10 minutes try to switch off everything, your antivirus, your firewalls, everything, and then see if you can receive data here. Then you have to configure your firewall to allow Hercules to open ports like this, then only you will be able to receive data here. Also open real term or any other terminal application for serial communication and open your debug serial port so that we can see the messages sent over the serial port by our STM32 microcontroller, so that we can know whatever going inside the microcontroller like this. And just debug your application, run your application, open both the windows, your Hercules window and your terminal window like this. and just execute the program, verifying downloaded successfully, and debug session started. Oh, right now it is writing that sorry, could not connect to server. And what is the problem here? I have not started to listen to this port here in Hercules. So just start listening to this port 5000 like this. It will show a message here. Just click the listen button like this. So now it is listening. Now we can restart our application. Sending data. See, data is received here on our terminal. So now let us compare this output with our program, source program. So here is the first message, connecting to server, and you can see this message here, connecting to server. And in the last run we have got a message, this one, sorry, could not connect to the server because we have not opened port 5000. And now in this session we have already opened the port, so it is saying like this, connected to the server, and here is the text, connected to the server. And after that it is starting the loop, and we can see the loop executing here. Sending data to the server, sent successfully 1 2 3 4 5 times, and finally it is closing everything. So our program is proceeding like this. So I hope that you are able to understand everything well, and you are able to carry out as I have instructed here, and also your program is compiling without any problem, and you are able to also communicate like this. So thank you very much for watching. See you in the next lesson.